In this problem, we're asked to approximate this definite integral of e to the sine x, which is impossible to do symbolically, by using a left-sided Riemann sum with n equals 20. So we're going to slice this interval -1 to 1 into 20 equal subintervals and measure the height of each rectangle at the left-hand side. And when we do that, it looks like this. Now we start setting things up for the sum. And what I do is give the name x0 to the leftmost point here, and then xn to the rightmost point. And I've taken n steps of delta x as I've gone all the way from the left to the right. So I would like to write down what delta x is. It's the total interval width, which is 2 divided by the number of subintervals that we sliced it into, and so I get 0.1. So every step is a step of 1/10. I then want a general expression for the ith cut point, and that's the starting point, x0, plus I steps to the right. So my starting point is -1. My delta x is 0.1, and so I can write this down as -1 plus 0.1 I. Now I need to start setting up the sum. And I find it helpful to write the area of the first rectangle, so I'm talking about the one all the way on the left. It just helps me to set up the indices for the sum correctly. And so my first rectangle, well, we're measuring its height from the left end of the subinterval, so it's going to be f of x0 is going to be the height times the width. So that's where my sum starts. My last term in the sum, you don't have to do this, but if it's helpful, you can. By the way, n was 20, so I'm changing xn to x20. In my last rectangle, x19 is where I measure the height. So I'm going to have f of x19 times delta x. And so I should be able to write down my area pretty quickly now. The area is going to be approximately equal to the sum as I goes from 0 to 19 of f of xi delta x, and then I can put in what's my function f. So I need to evaluate this function e to the sine x at xi, which is given by this little expression that we found for the cut points. So I end up with e to the sine of xi, which is -1 plus 0.1 I, times delta x, which is 0.1. Now I'm going to head to the computer algebra system to type all this stuff in and get an approximation. Okay, here I am in Maxima, and I put the sum in with the 0.1 out in front, times %e, which is the special symbol for e in Maxima, to the sine of -1 plus 0.1 times I as I goes from 0 to 19. I put the word float out in front, which gives us a decimal approximation, and I hit Shift-Enter, and I get about 2.19 for the estimate. One thing I'd like to point out here is that this is clearly an underestimate because e to the sine x is increasing on the interval that we're studying, but these rectangles whose heights are measured from the left-hand end of each subinterval are leaving a little gap. Every one of them is underestimating by a little bit. So it would be interesting to look at what a better approximation of the integral is. And we're going to go into Maxima again and use the quad QAG function for that. Okay, so we're back in Maxima, and we're going to approximate this integral using the quad QAG function. And I set it up as e to the sine x with respect to x as x goes from -1 to 1. And then you have to choose which algorithm in quad QAG that you want. And for our purposes, it doesn't matter. Any number from 1 through 6 for that last entry is going to be fine. I hit Shift-Enter, and my first number here is the estimate of the integral, and it's 2.28, slightly bigger than the one we just did, which we know was an underestimate.